Yes, we can hear you. Okay, perfect. Hi again, everyone. Welcome back. So we just finished our first and second set of faculty talks and student spotlights. So for the next session, the next half an hour, we're going to have a keynote by Rodney Brooks. Really excited to have him today. And then after that, we're going to have a third set of faculty talks, and then that will be the end of the program. All right, so with that, let me introduce Rodney Brooks. So I'm really excited to have him today with us as our keynote speaker. He got his PhD at Stanford and he did his postdocs at CMU at MIT. He was a faculty at Stanford and MIT and was directing the MIT AI lab and CSAIL until 2007. Rodney has founded 7 startups, including iRobot and Rethink Robotics, and he's now the CTO of Robust.ai. And he's also writing a book at the moment, which, in his words, is a deeply academic book on how AI and neuroscience might still be in their phlogiston phase in a hangover from 1945 to 1965. So with that, I'm really excited to have you with us here today, and welcome.
Thanks very much. Let me share the screen. See if that gets there. Is that there? Yes.
Yes.
Okay. So thanks so much for inviting me. I tried hard not to say any. This is a new talk, all new. No one's seen it. I tried really hard not to be too controversial, and I want to point out beforehand that I was asked to speak about, startups and the difference with academia. So what I'm going to do is contrast academia and startup life. I'm not saying one is better than the other, and academic life and academic problems are real. So when I'm talking about things, I'm really aiming them at startups. And I've got 3 messages today. No, why is that? No. Oh, maybe that. Yeah, 3 messages today. First one is, if you move from academia to startups, prepare to be disappointed, because the time it takes to do things can be very, very long, and the scope of what you can do is not as wide as you tend to think about in academia. It's much more narrow. Second thing is, if you want your research to be used in startups, then make things work in the most outrageously hard environment first. Don't leave that for later, and I'll explain why that's important. And the third thing is, you're gonna have to get over your theorem and formalism envy, particularly around optimality. That doesn't necessarily help much in real in companies that are deploying stuff in the real world. So there are different reward structures in academia and startups, and that changes the behaviors that you have to have. In academia, being smarter than everyone else is sort of important, or is deemed to be important, whereas in startups, building a great team is important. In academia, you want to, solving an open problem is a great thing to do. You get a great paper, you get a reputation, but in a startup, it's about selling lots of product. In academia, you want high H-index. Although I could quibble that doesn't measure everything, but you want a high H-index. In startups, you want a high margin. And the high margin is to sell one additional incremental copy of your product. What's the percentage of profit on that incremental? What's the margin on that? And in startup land, the more obscene the margins, the better. Google and Facebook have obscene margins, which is why they are valued so highly. And your depth is really important in academia. In startups, it's breadth. So if you want to, get your PhD thesis to a commercial system, or any particular paper that you've had in academia, you start off with this brilliant idea, the thesis or the paper, but that's really only 10% of what you need. There's another 90% to make that idea real. And once you've done that 90%, now you've got a robust demo and you can raise products for product development. And then there's another 90% on a much bigger base to turn it into a real product. And guess what? There's another 90% on top of that for manufacturing, marketing, sales, distribution, return, service, sustaining engineering. So if you're gonna go from doing a PhD thesis or being in academia and being CEO of a company, you're gonna have to deal with all these things if you want a robotics company to be successful. Oh, and there's one other little problem. Often, by the time you get to there, that brilliant idea it's not adding any value to the customer. We'll get rid of that. All the other stuff was what was important in what you built. So that's really disappointing. Your ideas may not get into the product. But the other thing is the time. So this is a paper I wrote in 1986, an internal memo at MIT. And I talked about building vacuum cleaning robots. And I said it wouldn't be a robot that looks like a person that carries the vacuum cleaner around. Rosie, the robot in Jetsons, was the people's view of a cleaning robot at the time. Said it will look like a vacuum cleaner that's been modified, and it could be insect level intelligence. So that was 1986. How it played out. First prototype in the lab in 1992, 6 years later. By the way, the computation system was from my company, iRobot, and it was hand built by me and the other two founders, Helen Grainer and Colin Angle. And then we donated it to the lab. That was 1992. 10 years later, we got the first Roomba product out. So now, it'll count at the bottom. We're 16 years in to get this first Roomba out in the world. And really, it was successful. I'll talk about that a little about that in a minute. But it wasn't everything. In fact, one of the problems with Roombas for many years was the user had to clean the brushes. And guess what? No users ever cleaned the brushes. So things got gummed up after a while. It was some clever mechanical design. Mechanical engineering is important for robotics. 2013 with self-cleaning brushes. So 27 years after the first publication, that's how long it took to get to really, I think, a successful product. It's a long, long time. By the way, the Roomba would have failed dismally, totally dismally, if it ever fell downstairs. We would have gotten sued up the wazoo. So what did we do about that? Well, this was a major research effort in the company. There's a view of the bottom of the Roomba. This is still, these things are still there today. There's triple redundancy. There's these cliff sensors, which are downward-looking infrareds, which detect a cliff. This front caster has to bear the weight of the robot, and if it ever drops, the robot thinks it's on a cliff and stops. That's clever mechanical design. The weight distribution was very tricky for that. And the third thing is wheel drop sensors. So when the side wheel does drop, it may be going off a cliff. Or if you pick the robot up, the wheels drop and it shuts down. So it's double duty there. It was a really fairly cheap solution in terms of the budget we had for cliff detection and not falling downstairs. Totally important. But this thing could never be an academic project. Some of the big problems, intellectually hard problems in robotics, in products, just won't fit as academic projects. There are different sorts of problems often. So that's the first message. Be prepared to be disappointed in time and scope. It's hard work. Now, physical robots in academia need to work for the duration of an experiment. In a startup, the robot you have needs to work for perhaps tens of thousands of hours. The market expectation at Rethink Robotics was that the robots had to run for 35,000 hours with no maintenance and no intervention from a user, if that was the case. They just had to work for 35,000 hours, which is a long time. No reboots, maintenance, etc. The physical robots in the lab are cared for by graduate students, and many of you who are on this watching this today know that, how much care and feeding it takes to keep the robots working. Whereas in a product robot, the owner thinks they paid too much, they don't care about how it works, they just want it to do the job. They have no care for the robot. In academia, you can have arbitrarily sucky startup interface full of Linux commands to get things running. In a product, it just has to work out of the box, and there can be zero cognitive load on the end user because they'll reject it as a product otherwise. And in academia, the audience, the people like us today who are watching these great talks and the great 1-minute clips, are fairly forgiving about pretend. Suppose this is the case, then this is the technique I'm showing now. Whereas in for a real product with end customers, there's zero pretending. It just has to work as it is. You can't say, well, suppose such and such. There is no debate, no argument like that. So what that means is, in a startup, the thing that you build is sort of academically disappointing and sort of dumb. And I went through this with my colleagues, who shall remain nameless at MIT, with Roomba. When Roomba started selling, they would say things like, well, that's not a real robot. A real robot would do X. And I say, does your robot do X? Well, not yet, but we're working on it. We're working on it. And, you know, that argument went on and on. And, you know, 30 million Roombas later, their robots still don't do X. But that's okay. They've done great research in the meantime. But you have to be prepared to deliver. And I tell everyone who joins my companies that you are going to be disappointed with how much we deliver compared to the vision that we have, because it's just got to work out of the box. But these things on the right here that you have to have for a startup imply certain things. It's, you know, they present a high bar. There it is. It says right there. That's a high bar. What is the highness about? Well, it's about environmental complexity. You can't get away with saying this robot will be great at tidying up as long as everything's on the tabletop that you want tidied up and they're all bright colors and easily separable in vision. You have to deal with clutter. You have to deal with real mess, real homes, or wherever, real factories, whatever it is. You have to deal with environmental complexity. You have to get over that high bar. Because below that, it's not going to be a viable product. People aren't going to buy it. Oh, now I have to, you know, clean up for the robot all the time so it can do its job and it's supposed to relieve me of something. No, you have to get that high bar. So there's another axis here though, and that's task complexity. Ideally, you want this gold star here. You want your robot to be doing complex tasks in complex environments. That's what you want. That's your long-term view. But how to get there from the starting point when you start your company? From the robot doesn't do anything and it doesn't really work in any environment. Well, I think, I hope my mouse is visible here. Around this star, if you're moving in this space around here, it's a really high gradient, no matter which direction you approach this gold star from. It's going to be a high gradient. Well, you could try to get there by first demonstrating complex tasks and then ramp up the environmental complexity. But maybe you run out of money before you get to this, or during this really steep ascent. There's another vertical bar here, actually, over what is sort of minimal in terms of the task that could be of value to an end customer. And so another way of thinking about it is to take this path. First, work on getting the environmental complexity before you get over here to this really steep space, so that you get across this vertical here to where it's both a viable product in terms of environmental complexity, and it does enough task for someone to be excited, or enough people to be excited to buy it. You know, then you can keep going here, but hopefully by now you've already got revenue and you're less likely to run out of money as you get to this gold star. And by the way, you know, as I showed before, that could be you know, in my case, it was a 27-year process to get there. I recommend, if you want your research to be used in industry or used in a startup, rapidly go towards the complex environment in which it's ultimately going to have to run before you get too fancy and show off. Oh, look, it can do this, it can dance, it can use a hula hoop or whatever. I'm joking there. But go for environmental complexity over task complexity first. And that's hard work, but it lets you be in a space where you can generate revenue before you die. So if you want your research to feed into a startup, favor robustness in complex environments over complexity of tasks. that's, I think, my most solid piece of advice for today. By the way, I've been talking about customers and how important they are, and they are important, but man, oh man, customers are pains in the butt. There's irrational, there's tension with customers. So the current irrationality that is being seen by a lot of robotic startups, and it was certainly seen by my previous one, Rethink Robotics. And I'm sure that some of the faculty, I know that some of the faculty who presented earlier today have seen this in their startups, that the customers want a single robot doing a task that was previously done by a human at the same speed or better as a human. Well, you could put 2 robots in there and you get the throughput. Now, there's a cost issue, but it doesn't necessarily, from a rational point of view, have to be as fast as a human. But this is what we keep seeing in customers in manufacturing robots and pick robots. So, well, how did Roomba get away? Because it wasn't a great cleaner. How did it get away with not cleaning as well as a human? Well, fortunately, our early market was people, often grad students, who didn't clean their apartments at all. So we didn't have to compete with someone who cleaned well. We just had to, if we took a bowl of dirt out of the apartment once a week, it was way, way cleaner than not. So we were competing with 0, not competing with a human. And that, partially that was because it was it wasn't a green field if they were dirty apartments, but you get the idea. There is that. But here's the second point: make things work in the most outrageously hard environment first. Is my advice. Theorems and formalisms in robotics. Now, I just want to point out, I was trained as a mathematician. I had a classical Eastern European education in mathematics. In fact, I don't know if Rosina is on, but Rosina and I actually shared the same analysis professor. She learned from him in Bratislava, and I learned from him in Adelaide, Australia. So I love theorems, I love formalism. Some of my best friends are theorems. I'm not biased against them, as people say. But they're usually not worth the cost of their assumptions, because formalisms and theorems come with assumptions about the world. And making those assumptions true is often a very expensive thing, and maybe it's too expensive for you to work in a complex environment and have them true. If the assumptions are not true, then the theorems are not worth as much as you thought. So the implicit assumptions that many theorems and formalisms in robotics are that actions in the world are about things rather than coordinates. And by the way, most of the big industrial robot companies are not there yet. They're still talking coordinates for industrial robots rather than things, but everyone here today has been talking about things. Actions can be atomized or atomicized as an assumption that people have. Things in the world are perceived, things that are stable in the world are perceived as stable in the world, but we all sort of know that's not quite true. And there's another assumption, which is less made today, that the world is static except for what the robot does. And this has been known for a long time. This is the Shaky team at SRI in Menlo Park in the late 60s, early 70s, the robot Shaky. And not dissimilar to some things I've seen today, the environment of Shaky was fairly clean with well-colored matte objects rather than being complex environment. This is a screen capture from the Shaky movie. I recommend the Shaky movie if you haven't seen it. If you go to my MIT website, it's ultimately there. But that's Richard Fikes on the left, Bertram Raphael on the right. I'm not sure who it is sitting down, but they're doing the triangle table for strips planning. And I'm sure most of you have seen a strips planner-like thing where these atomic actions, preconditions, postconditions, etc., but atomic actions. And that's how all the publications were about Shaky. But there was another truth below, which turned up in some internal reports, and Nils Nilsson put them together into an external report when he was at Stanford in 1984, that there was some other dirty secrets inside Shaky. At the bottom, the low-level actions were just, sort of motor commands: roll a certain distance, pan the camera a certain direction, etc. But in between those low-level actions and the strips planner, the macrops and planex, were these things called intermediate level actions. And I actually didn't know about these till much later. They just weren't talked about. And these intermediate level actions, and here's the simplest one I've found, it's not one of these actually, because the publications were different at different times, were finite state machines with no guarantee on termination and no guarantee on how long they would take. If you look at this, on the left, there are labels for the states. There's a predicate. When you're in the state, if the predicate is true, you do the actions, none there, and then go to the next state. And these are returns that here you jump around in a loop between 4 and 2 and 3, doing various sensing, calling other intermediate level actions. You know, and this was there. And I sort of look at this, the purpose of these was to mush time and actions into looking atomic to the high level planner. And we still do that. All our systems do that. And by the way, there's Charlie Rosen, who's head of the project, dressed as a gremlin in the movie. He comes and invisibly moves something around. And even though there was a static world assumption, these ILAs enabled it to be robust to some non-static things. So that was what happened in Shaky, and it happens in all real robot systems. There are these things that mush stuff into the higher level assumptions. But, you know, we also have that in perception. Deep learning labeling has confused us to think we have symbol grounding solved, but in a sense, we don't really yet. There's also problems of stability of the grounding, which involves ongoing perceptual smoothing and integration, and all real systems have that somewhere. Brian Cantwell Smith has written a really good book about this. For those of you who've read any of his previous writings, like his 800-page PhD thesis or his mid-90s book on objects, this is not as bad. It's only 150 pages, but I still, as a native English speaker, had to go to the dictionary all the time to figure out a lot of his words that he uses. But it's a deep book, and it's interesting. And he calls this process, or this thing, of the process of registration. It's richer than grounding that we actually have to do to make things work in our robots. So all execution systems have something like intermediate level actions or intermediate level perceptions. I just made that up. And they're a mechanism to maintain the assumption of the theorems. But the assumptions are not necessarily met. These ILAs and ILPs sort of let you pretend about the world, that it's stable, and then not really. So often, certainly optimality theorems, which are often fairly unstable on their based on their assumptions, don't work out so well and not so useful. And so for all the robots I've built and delivered to homes, factories, planetary, roving, military, and even the robots that shut down Fukushima, they all intrinsically assume that everything is unstable and try and compensate for stability at all times. And having an optimal algorithm is usually not good enough. To get something that's good enough, then it's optimal. And so this is sort of a recast, the play on words here, a recast of Herb Simon's satisficing description. Herb was one of the founders of AI, one of the 4 principal founders of AI, also won the Nobel Prize in economics, that satisficing, good enough is what you need, and how you get good enough. And enlightenment in the world of deployed robots, and I'm not criticizing academia here, I'm saying for deployed robots, your enlightenment comes from empiricism, measuring, testing for thousands and thousands of hours, rather than from proofs, which I liken to faith because the assumptions are so unstable. So that's my third message I wanted to say today. And as I was writing the slide, I realized that, you know, the second message here, I was saying, you know, don't pretend, no pretension. And the third one is no pretension in industry. With that, I want to finish, but I do want to say that Robust AI is hiring. We've doubled in size since COVID hit. We're a distributed company, and we want to double in size again now. So send email to Rodney at robust.ai. I'm not sure you can see it right there on the right. That's Rodney at robust.ai. If you're interested in, if these messages I gave today didn't scare you off too much and you want to work in industry, we would love to talk to you, and be safe in the meantime. And with that, I think I'll switch to questions, and I don't quite know where I'm going to get questions from.
All right, thank you so much for such an inspiring talk. That was awesome. All right, so let me just look at questions over.
By the way, in industry, people aren't as polite as you are. Thank you.
Try to be polite. Okay, so actually, let me ask a question first, and then I'll get back to the YouTube one. So, so like you talked about good enough. Like, who defines good enough? Like, for example, when you think about autonomous cars, right? Like, when is it good enough? Who defines like when is this good enough? Like in general, when we are thinking about these problems.
Well, you know, in the case of autonomous cars, and I've been writing about this for years, the assumption that there was going to be a one-for-one replacement in our existing road network with human drivers on the road at the same time says that good enough has to be human level performance. And we're not going to get there soon. We're only going to get to autonomy by working in restricted environments. And we see more and more people talking about working in you know, enclosed, geographically localized places where all the other drivers are trained, you know, a campus-like environment where the public can't drive on there. So that you know, as a startup company, you have to look at where you're going to sell, whether it's software or physical robots, and what the environment is going to demand, and then and talk to customers early on, and from that get an you know, an empirically testable notion of what's good enough. Autonomous driving did not do that. That was not the way it was. And you know, there was a story in the information last week that Uber regrets wasting $2.5 billion on it. I could have got a not working system running for much less than $2.5 billion. I would have been happy to waste less money. It would have been cheaper. But, yeah.
All right, cool. So we have a couple of questions. Let me actually, Erdem has a question. Do you want to, Erdem, ask your question?
Sure, yeah. I was asking, like, do you think if it makes sense to try to bring academia closer to industry, or is it better to have like all these differences between the two?
I think the difference is healthy in many ways, because companies can't be as innovative as academia can, but one has to understand, and it only works in countries where there's funding agencies which are tolerant of failure. Most things are going to fail. Most things are not going to be used in the real world. Most things may trigger some thought years later, but they're not going to be used. So you have to be tolerant of a very high failure rate. You know, in the US, we have the venture capital system, stronger here than many other countries, and they pride themselves on being tolerant of high failure rates, but they're nothing like the failure rates in academia. And so when I was last at MIT, I was always trying to figure out how to raise funds to do truly outrageously weird academic stuff, but I could never get my academics to agree to it, and they would never let a graduate student do truly outrageous stuff. The only place that seemed possible to get truly outrageous ideas looked at was with undergraduates. And then when undergraduates realized they needed papers to get into one of the best schools, that went away too. So we're, you know, the scale of academia is sort of killing the risk, what I think is the high risk stuff, which is probably the best thing that academia could do. Be riskier. Graduate students out there, ignore your professors, do risky stuff. No.
Thank you.
All right, so we have a question from Ken. So Ken is asking, before I order Cantwell Smith book, can you say more about how registration differs from grounding?
Yeah, it's about the, he uses a bunch of examples, but it's about, and I recommend Smith's book just to improve your vocabulary. You know, that alone is worth it. But his registration is about what the ongoing relationship between the observer and the object is, and how it may change through different perceptual systems at different times, and what is the essence of the objectness that is there. His point has always been, in his 1995 monstrous book, which is, I don't recommend, it's really hard to read, was that we tend to think of objects as just being there, but objects are one of the great inventions of human minds, and they have to be likewise maintained and invented in our AI systems. By the way, I was surprised in this new book, 2019, about Brian's generosity towards deep learning. I wasn't expecting that. So don't be scared, that he's going to say deep learning is bad, don't do it. He doesn't say that at all.
All right, I have a question.
Goldberg?
Sorry, what?
Who was that? Was that Ken Goldberg?
That was Ken Goldberg, yes, yeah.
Yeah, Ken, you can read big books, it's okay.
Cool. I have a question from Claire Tomlin. So Claire is asking, what do you think should be the fate of theorems in robotics?
Well, here's the problem. Theorems and optimality, you get to, too often you get to choose, what it is you want to optimize, and then you get to choose the norm that you use. And it's often driven by getting a theorem rather than by having something really work in the world, which is why not so useful in industry. I know that I know better than to say academics shouldn't prove theorems. I'm not going to say that.
All right, so I have a question from, I think, one of the students. So Adi is asking, so as Roomba is joining dishwasher and laundry machines as one of the most successful robots in homes, what is next? And also, she's also asking, what took 27 years? Is it building consumer product, or which part of it that was actually taking 27? Well,
it was a whole bunch of things. Some was, I'll answer the 27-year question first, and then the what's next. It was a bunch of things. Like, we had that product on the market from 2002 until we figured out how to make the brushes self-cleaning. It just took it was clever mechanical design, and it just took a lot of work, a lot of internal research to get there. When I first talked about the idea, we didn't have the technology to build a prototype even. That was 6 years later when we could finally get enough stuff off the shelf to build the vacuum cleaner. By the way, the bad thing about that vacuum cleaner was it was designed by computer scientists. It sucked the dirty air through the computer boards, which was not a good idea, but it was enough for a pretend and a demo. But to get from that to a product which retailed at $200 was another big project. We were not the first robot vacuum cleaner on the market. The Electrolux had the Trilobite, which, by the way, Henrik Christiansen had worked on, and it sold for 2,000 euros. We didn't think many people were going to buy a 2,000 euro vacuum cleaner in 2002. We went around to shopping malls and we asked people by themselves, how much can you blow on a impulse purchase for a gadget without your spouse divorcing you? And the answer came out around $200. And so that became the first thing that we had in a big spreadsheet. The bottom right-hand corner was $200, backed up all through, all the costs, et cetera, for the bill of materials, and then designed that bill of materials. And that was a long, hard process also. That's why it took so long. Getting the price point and getting the usability of it. What's next? I don't know exactly what's next, but I know that there is going to be a tremendous pull because of the demographic inversion of letting people stay in their homes longer as they get older with dignity and independence. And anything that can help that will be important. What those if they're, we've got lots of products which are not robotic, which help the elderly remain in their homes longer. If there is something in robotics that can help, maybe in one of the real biggest reasons people have to leave their home and go into managed care is when they can no longer get into and out of bed by themselves. Maybe it's a robot that helps people get into and out of bed. I don't know.
Okay, thank you so much. So I think we are out of time. So with that, let's normally, if it was an audience, like we had an audience, I would ask. Let's thank Rodney. We have more than 200 people watching, so I think they're thanking Rodney virtually. And I think we can basically, yeah, take a break now for 15 minutes. And let's try to be back at 12:15 for the last set of faculty talks. This is the last part of our program today. Thank you again, Rodney.